All right, so we are going to talk about the time memory trade-off attack on A51 stream cipher. So let's recall how everything works. So there is a state which is initially filled with zeros, right? So 64-bit state A51 cipher, right? So what we do is we feed 64-bit key, right? Now I have a state that is different than all zero. Then what I do is feed 22-bit frame. So I have a new state. And this 22-bit frame is not a secret info, but it is determined when you call somebody, right? So we are talking about A51 stream cipher, which was a standard in 2G, but nowadays we still use it because base stations might be old. The GSM operator might force you to use it. Actually, GSM operator might force you to talk in plain text, by the way, which you never notice because your phone doesn't inform you which cipher you are using, right? So, but if the person you are calling has a very old mobile phone, they wouldn't support A53, so you will be using A51. So when we call somebody, actual key stream generation process starts. The secret key 64-bit is fed into this state, then 22-bit frame is fed, then this is run for 100 more clocks to determine the initial state. Okay, let's call this initial state. Okay, I couldn't write it from here, but let me write it in a more readable way. Okay, initial state. So from this point on, actually you provide key stream. Okay, so since this is 22 bits and this is 64 bits, performing an exhaustive search and storing every key stream would take a lot of place. But what we can do is as follows. We can write every initial state, since they are 64-bit, we can write every 64-bit initial state, right? Like this. And go until all ones, okay? So as integers, this is 0, this is 1, this is 2, this is 3. And this is 2 to the 64 minus 1. So you can put every initial state to this A51 cipher and run A51 cipher, stream cipher, for instance, 64 clocks to produce 64-bit key stream. And let's call this one key 0, and this one K1, K2, K3, until K2 to the 64 minus 1. So assume that we also kept only 64 bits here, okay? You can create, of course, larger key streams, but we are going to focus on 64 bits. So this means that if you perform this exhaustive search, you break the cipher because you capture a key stream and check which key stream actually belongs to which initial state. But so we can perform the exhaustive search whenever we want. Question is, can I do it once and store everything? So if you try to store everything, you need to store 2 to the 64 values here. And all of them are 64-bit. So you actually need 2 to the 70 bits as a memory to keep all of this table. But this means that actually 2 to the 67 bytes, right? If you subtract 10, this is 2 to the 57 kilobytes. Similarly, it is 2 to the 47 megabytes, 2 to the 37 gigabytes. I guess I haven't missed anything, right? Byte, kilobyte, megabyte, gigabyte, 2 to the 27 terabytes, and this would mean 2 to the 17 petabytes. So we don't have this much storage. So this is the problem. I cannot perform an exhaustive search once, store everything in a table, and then break every A51 communication instantly. right? Because I don't have the storage as this much. So question is, can I keep a very small amount of this table, but still break every A51 communication? And time memory trade-off attacks actually comes into play here. So let's erase all of these parts and let's show how we can perform an time memory trade-off attack. So let me erase this part. So let's say that we have limited amount of space. So instead of calculating all of this, let's calculate a smaller part of it, okay? So let's say that you have only 2 to the m places. So assume that you have a hard drive of 4 terabytes. I think nowadays it is easier to buy 8 or 16 terabytes. So let's say that I can only store 8 terabytes, let's say, okay? 8 terabytes. So this means that you will start with many zeros, but a lot of ones like this, okay? So you have n many ones, but this in total will be 8 terabytes, okay? So just calculate what the m is. I don't want to do it right now, but assume that. So I only store this many initial states. So this is 2 to the m minus 1, okay? So as you can see, 8 terabytes is very small compared to the 2 to the 17 petabytes, right? So if I only calculate the key stream generated from here, which will be again K0, so let's say this is A51 encryption, K1, K2, K3, and I go until here and store K2 to the m minus 1. So if I keep such a table, you only can listen to a small fraction of encryption, or sorry, a small fraction of communication, right? Because you should be very lucky and the key stream you capture is inside this table. And most probably it wouldn't be, because 8 terabyte is compared to very small, compared to 2 to the 17 petabytes, right? So this approach makes no sense at this point. So what I suggest is to go further. So instead of keeping these values, just assume that these are, again, initial states and perform A51 encryption, assuming that these are initial states, and produce key stream from these states. Okay, so this time produce, for instance, K02. Okay, maybe not use parentheses. So K02. This is K12, K22. So these are ones. Okay. K31, sorry, 2. And this way you get K2 to the m minus 1, 2. Okay, so now I have more values, right? Because now, for instance, if I store both of them, I will be listening to more communications, right? But of course, if I store both of them, now instead of 8 terabytes, I need 16 terabytes. So my aim will be to only to store this final one, but this would increase my chances of capturing all of them. Okay, and I will explain this how this works, but let me show it further. So let's continue. Perform encryption again, assuming that these are also initial states. So I write K03, K13, K23, K33, and until K2 to the m minus 1, 3. So I repeat this process many, many times until I reach to a place called K0n. So I repeat this process n many times, okay? So you end up with K1n, K2n, and go K2 to the m minus 1 n. So one step before we have K0 m minus 1, K1 m minus 1, K2 m minus 1, and you go this way until K2 to the m minus 1 n minus 1. So assume that I performed a lot of encryptions here. So the values, the number of values in total actually exceeds 2 to the 64. So assume that I performed the exhaustive search on all possible initial states, but all of those states are not here, but they're scattered around here. Okay? So if I increase n really large, so aim is to have such that 2 to the 64 is smaller than 2 to the m times 2 to the n, right? So which is, 2 to the m plus n. Clear? Because this, I have 2 to the m times 2 to the n many values here, right? M many values, sorry. So this will be, maybe it should be like this. Sorry. Yeah, this would be n, right? Because this table actually has n times 2 to the m values, right? Okay, so aim is to increase n so that this number exceeds the whole exhaustive search. Maybe with multiplication with a constant like 3 or 4. So assume that I did this. So now, again, I have values here which now exceeds 2 to the 17 petabytes, right? So actually, I didn't gain anything from the storage if I store all of these values. So what I propose is that only store this part, okay? It is 8 terabytes, right? So idea is simple. Store these 8 terabytes on a hard drive, put an ARM processor on it, put an antenna, listen to the communication. So put this device on your backpack while walking, listen to the communications, capture the ciphertext, you get some part of the plain text, XOR it, you get the key stream. So just check if that key stream is here, okay? So if you are very, very lucky, and note that a mathematician is always unlucky, but assume that you are really lucky and it is here. So you know that this key stream is here, okay? So now you know that this key stream is generated from this initial state, but you haven't stored it, right? But you know that this is the second value. So you go here, okay? Perform A51 here, 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 and you obtain this value. And say that, okay, this is the initial state to produce this key stream. So this way, you, instead of, if we had the whole table, we would directly learn this value. But instead, we had to do n many encryptions to obtain this value. So this is the time memory trade-off. I reduced the memory from 2 to the 17 petabytes to 8 terabytes, but instead of a single table lookup, I performed n many encryptions to obtain this initial state, right? But again, this was for the scenario where we were lucky and the captured key stream was inside this table, which generally never happens. So let's go back and consider the unlucky case. So you obtain a key stream, and let's say that it is here, okay? So this is the key stream you captured. So you look at this key stream and check if it is here, because this is the table you keep, right? And it is not here. Right? So you captured the key stream, let's say K prime, and you look at if K prime is here. So it is not here because it is here, and I didn't store all of these values. So now what you do is as follows. Perform A51 encryption to this K prime. So as you can see, it will give you K2n because it will hit this one. Now I know that it is here. So I go back. This time perform m-1 encryptions, obtain this value, and say that this initial state produces this key string. So this way, I solve the problem. But it wouldn't, most of the time, it wouldn't be here, but maybe it will be here, right? This is the thing you captured, but you never stored it. So what you do is as follows. Now this time, let's say it is K double prime, and it is this. So you look at this table and check if K double prime is there. It is not there. Perform A51. Okay, you obtain K double prime. Let's say, I don't know. Let's say 1 here. So because once you perform this, actually you are here. Okay. You check this value if it is here, but it is not. You perform another encryption. It is now here. You check this value here, but it is not here because it is here. You do it again and again and again. You do repeat this n many times. Okay. After n many times, you hit K0n here. So you know that it comes from here. So you can perform n-1 encryptions and check this. Okay. Actually, sorry, once it hits here, you know that it is from here. So you actually know that initial state is here. Sorry for, yeah. So I made a time memory trade-off. But of course, there might be some problems because here, there might be repetitions. Think about it in this way. Maybe, okay, let me change the color for that. Maybe this value is identical to this value. This can happen, right? So actually, at this point, keeping this rest of this table makes no sense because it is already included here. So you are actually wasting some storage. This is why I said larger. This value should be larger than this because there will be repetitions. Okay. So you cannot solve this problem by choosing this number 2 to the 64. I mean, you should be very lucky and there shouldn't be any repetitions for that to work. This is why we, multiply this number with a constant like 3 or 4 and generate a larger time. So this means that actually you increase the number of n's. If you keep smaller n, the chances of you decrypting the communication become smaller. If you increase the n, this means that when you're constructing this table, you need to perform more encryptions, right? But this is related to your computational power. If you have a lot of modern GPUs, performing 2 to the 70 encryptions actually wouldn't be a problem for you. So you can keep this n really large. And with 8 terabytes, you can solve this. But similarly, if you buy a 16 terabyte hard drive, so 2 to the m, will be doubled. So you can keep the n to this. So it depends on your storage and computational power. We always say that computational power is easier to reach than, memory. And here it depends on your storage. I mean, if you want to carry it with your backpack, of course, you can buy a single hard drive. But if you want to do this operation on your server, having maybe hundreds of or thousands of terabytes might not be a problem at some point. So you can keep this table really large and increase the n or make it smaller. It is your choice, right? So this was the main idea. So what I simply did was to choose some initial values. So one way to do it, instead of choosing it like this, you can actually randomly choose this one. It would be better. And when you perform A51 encryption and obtain these values, maybe considering them as the next initial state, you can perform a small operation on them, like put them into a function like fx equals to x squared plus 1, for instance, to make it more randomized. So rainbow tables and so on actually has this kind of many ideas. So there are many different methods to perform time memory trade-off attacks, but this is the basic idea.